the position of a point, and the number of tangents. To begin, let's establish our foundation. In the study of circles, we often encounter a specific type of line called a tangent. A tangent is defined as a straight line that touches the circle at exactly one single point. It doesn't cut through the circle, it just grazes the edge. This specific, unique location, where the line and the circle meet, is a very important term in geometry, and we refer to it as the point of contact. Now, here is the core question we will be answering today. How many tangents can we actually draw? As we move through the next few slides, you will see that the answer isn't always the same. The number of tangents that can be drawn to a circle depends entirely on where our starting point, let's call it point P, is located in relation to the circle. Is it inside, on the boundary, or outside? We are about to find out. Welcome, everyone. Today, we are going to explore a fundamental concept in geometry, the position of a point and the number of tangents. Point inside the circle. Suppose we have a point, let's call it point P, and this point is located within the interior of the circle. If point P is inside the circle, it is actually impossible to draw a tangent that passes through it. To understand why, let's look at the detailed reasoning. Remember our definition from the previous slide. A tangent must touch the circle at exactly one point, and crucially, it must not enter the interior of the circle at all. However, if you try to draw any straight line that passes through point P, since P is already inside the circle, that line will inevitably enter the circle at one point and then exit through another point on the opposite side. When a line intersects a circle at two distinct points like this, we don't call it a tangent. Instead, we call it a secant. So, to wrap up this case, because any line through an interior point must hit the boundary twice, every line drawn through point P will be a secant, and therefore, 0 tangents are possible. Now that we've established what a tangent is, a line that touches a circle at exactly one single point of contact, let's look at our first specific scenario. Now, let's move on to what happens when that point moves from the interior directly onto the boundary of the circle. Point on the circle. Imagine, instead, that the point P is not inside the circle, but lies exactly on the circumference, which is simply the outer boundary of the circle. In this specific case, there is exactly one tangent that can be drawn. To understand why this is the case, let's look at the detailed explanation. Since point P is already sitting right on the edge of the circle, the tangent we are looking for is the unique line that touches the circle specifically at that point P without ever entering the interior. There is a very important geometric property to remember here. This tangent is always perpendicular to the radius that is drawn from the center of the circle to the point of contact, point P now. Think about the geometry of a line. At the very end of a radius, there is only one possible direction you can draw a line that stays perfectly perpendicular to that radius. Because there is only one unique perpendicular line possible at that specific endpoint, we are left with exactly one unique tangent at that point. Now that we have established that a point inside the circle allows for no tangents at all, let's move on to our next scenario on slide 3. This sets the stage for our next slide, where we will see what happens when we move point P even further away into the exterior of the circle. Point outside the circle. Now, let's move on to our third scenario, which is often the most interesting one to visualize. What happens if the point P is located in the exterior of the circle? In this case, we can draw exactly 2 tangents from point P to the circle. To understand why this is the case, let's look at the detailed explanation. Imagine you are standing at this external point P and looking toward the circle. You can draw 2 distinct lines that just graze the edge of the circle on opposite sides, one on the left and one on the right. Each of these lines will touch the circle at exactly one specific point. Let's label these points of contact as T1 and T2. Now, a common point of confusion is thinking there might be more. While it is true that you can draw infinitely many lines from point P that pass through the circle, which, as we learned in the previous slide, would be called secants, Only these two specific lines satisfy our strict rule of touching the circle at exactly 1 point. As we will see in our next few slides, this concept is exactly like a satellite in orbit looking down at a planet. Real-world example, the satellite observation. Now that we have covered the 3 geometric cases, inside, on, and outside the circle, let's step away from the abstract diagrams and look at a real-world analogy to help solidify this concept. Imagine, for a moment, a circular planet floating in space with a satellite positioned somewhere in its vicinity. We can use the path of a signal sent from this satellite to visualize the number of tangents possible. Let's look at our first hypothetical scenario. Scenario A, where the satellite is located inside the planet. Now, I know this is purely hypothetical because, in reality, a satellite wouldn't be inside the planet's core. But if we assume the satellite is positioned deep within the interior of the planet, think about what happens when it sends out a signal in a straight line. Because the satellite is inside, any straight-line signal it transmits must travel through the planet's interior and eventually exit through the surface on the other side. This means the signal path will necessarily hit the surface at 2 distinct points. As we discussed in our second slide, a line that intersects a circle at 2 points is a secant, not a tangent. Therefore, in this specific scenario, the result is that no tangent is possible. Real-world example, satellite on the surface. Now, let's move on to our second real-world scenario to further illustrate this concept. Imagine, instead of being buried deep inside the planet as we discussed in the previous slide, our satellite is now resting directly on the surface of the planet. In this case, the satellite is positioned exactly on the circumference of our circle. If the satellite sends out a signal, it can send it in one specific direction that perfectly grazes the surface at that very spot, without ever entering the planet's interior. Because any other direction would either go into the planet or move away from it, there is only one unique path that stays tangent to the surface. Therefore, just like a point located on the boundary of a circle, our result is exactly 1 tangent. This perfectly mirrors what we learned earlier regarding a point located on the circle. Real-world example, satellite in orbit. Now, let's move on to our final real-world scenario, which is perhaps the most common one we see in space exploration. Imagine scenario C. The satellite is in orbit, meaning it is positioned in the exterior of the planet. In this case, the satellite is at a certain distance from the planet's surface, clearly outside the circle. From this external position, the satellite can send out 2 distinct signals that just graze the edges, or what we might call the horizons, of the planet. If you visualize this, one signal will graze the left side of the planet, and the other signal will graze the right side. Because these 2 signals touch the circular boundary at exactly 1 point each, they represent our 2 tangents. Therefore, the result is exactly 2 tangents. This perfectly illustrates the rule we discussed earlier for any point located outside the circle. Common mistakes to avoid. First, let's talk about the confusion between secants and tangents. It is a very easy mistake to make. You might see a line starting from a point and touching the circle and instinctively label it a tangent. However, you must be very careful. As we discussed in our second slide, a tangent must touch the circle at exactly 1 point. If the line you are looking at enters the interior of the circle and hits the boundary at 2 different points, that line is actually a secant, not a tangent. Always check the number of intersection points. Second, there is a common misconception regarding points located outside the circle. Because we know that from an external point, labeled as point P, we can draw an infinite number of lines that pass through or near the circle. Some students mistakenly assume there must be an infinite number of tangents. But remember our discussion from slide 4. While you can indeed draw infinitely many lines from point P, most of them will either miss the circle entirely or, as we just learned, act as secants by cutting through the circle. In reality, there are only 2 specific, unique lines that perfectly graze the edges of the circle. Now, before we wrap up and look at our final summary, I want to pause and address two very common pitfalls that I see students fall into during exams. It is crucial to master these distinctions to ensure you don't lose marks on technicalities. Keep these distinctions in mind as we move to our final slide for the key takeaways. Key takeaways. All right, we have reached our final slide, where we will summarize everything we have learned today. This table serves as a quick reference guide to help you remember the relationship between the position of point P and the number of tangents possible. First, let's look at the case where point P is inside the circle. As we discussed earlier when looking at the secant lines, if the point is in the interior, the number of tangents is 0. In this position, all lines passing through the point are actually secants because they must enter and exit the circle. Next, if the point P lies exactly on the circle, we have exactly one tangent. This is that unique tangent we identified earlier, which is perpendicular to the radius at that specific point of contact. Finally, when the point P is located outside the circle, we can draw exactly two tangents. These are the two distinct lines that graze the edges of the circle, much like the satellite signals we visualized in our orbit example. If you can memorize this summary, you will be able to solve almost any problem regarding the position of a point and tangents to a circle. Great job today!